Okay. Well, I'm not really an expert on QCD. I'm more working in the astrophysics side. Okay. So today I'm mainly talking about trying to determine mass and radius values for neutron stars from observations of millisecond pulsars. And the equation of state constraints are something I'm interested in, but I'm not really the expert at all on equation of state. Okay, so this is a project that I've been working with Sharon Morsink over about 4 years now, along with some of her graduate students. Okay, so first say a little bit about neutron stars and why we're interested in mass and radius. Then explain why pulse shape modeling is a good way to find mass and radius. And then say why millisecond X-ray pulsars are particularly good for this. I'll spend a little while talking about the actual calculations and just the procedure for modeling the pulse shapes. Then a little bit about the results for 2 of the millisecond X-ray pulsars. There's only about 8 or 10 in total known, but most of them are too faint to really work with. And then lastly, about equation of state. Okay, so this is a diagram from one of the many presentations by James Latimer on structure of neutron stars. We don't really know what the interior of neutron stars is made of, and this diagram illustrates 6 or 7 of the possibilities. 6, I guess. Okay. So the traditional neutron star, well, we know very well how matter behaves at low density, so the outer part of the star is well understood. You have some surface, and basically it is solid at the surface with a density of about 10 to the 6th, and consists of nuclei plus electrons, and the actual structure will depend on magnetic field, but we're not concerned about that. And as you go deeper into the crust, the electrons become more degenerate, and the Fermi energy rises until at about 10 to the 11th grams per cubic centimeter, the Fermi energy of the electrons is high enough that neutrons, electrons and protons are more stable as neutrons. So you get what's called neutron drip, and below neutron drip, the neutron fraction increases, and it increases until the nuclei are totally dissolved. So at that point, you have neutrons, protons, and electrons mainly, but the reason all your protons and electrons don't recombine to neutrons is neutrons become degenerate. So that raises the Fermi energy of the neutrons, so you always have some fraction of protons and electrons, not just pure neutrons. All right, and then things become more uncertain when you become at density high enough that you reach what's called nuclear saturation density, which is basically just the normal density in heavy nuclei like iron or lead. All heavy nuclei have roughly the same density under 0 pressure, and when you get up beyond that density, we don't really know what happens because of many body effects in nuclear matter. Okay, so in the simplest case, it just remains neutrons, protons, electrons with a mixture of muons because of the high Fermi energy right to the core, but it's equally feasible that we get other states of matter occurring, for example, higher mass baryons or pions or kaons. So you have different types of condensates which occur in the center, which drastically affect how the pressure behaves, as well as other processes like neutrino emission properties. Now, back in I don't remember the year, Chris would know that, Ed Witten made a hypothesis that strange quark matter would be the absolute ground state of matter, which just means that if you manage to convert baryons into quark matter, this quark matter would be the lowest energy state of matter and would be stable even at zero pressure. Whereas the reason we have neutrons inside the neutron star is because of the high pressure raises the Fermi energy of the electrons and converts protons to neutrons. So that you depend on gravity to provide pressure to make neutron stars stable. But if quark matter is the absolute ground state of matter, then once you convert it, it stays like that. And even if you took away the gravity, you could get things like quark nuggets floating around in space and lots of other things. Okay. So there's lots of possibilities. We don't really know what's going on at high density. And the idea is to try to find out something about this by looking at neutron stars. And that this diagram doesn't have the same scale, so there are different radii and different masses for all these objects. Okay, so we can take any equation of state, which is basically just the well, it's not simple, but it basically tells us the pressure, energy density, and pressure at any given point in the star, and use the relativistic versions of the stellar structure equations to calculate the total mass and the total radius of any configuration. Okay, so you just have a whole set of these curves for any given total mass and outer radius, and then you given the equation of state, you can only get a one-dimensional set of solutions to this equation. Okay, so this is a plot. Forget about these other curves. I'll say something about them later. So typical neutron star equations of state start at low mass, at large radius, and as you increase the mass, the radius decreases. So that's reminiscent of white dwarfs, and that's a property of degenerate matter. The quark star equations of state are very different in the sense that as the radius increases, the mass increases. Now, they have some simple behavior. So the quark star at low mass, the effects of general relativity aren't important, so the mass goes as r cubed. They basically behave like constant density spheres. And then as you approach the limiting mass, of course, they become unstable and collapse into a black hole. So it turns over. For the neutron stars at low density, well, they very roughly behave as a non-relativistic degenerate gas, but not quite. And again, at high mass, the general relativity turns over. So there's two different, totally different classes of equations of mass radius curves for different equations of state. Ones which decrease in radius as mass increases, and the others which increase in mass. Increase in radius as mass increases. Here's another diagram from Latimer, where, again, we've got a bunch of equations of state in black for neutron star equations of state, and then these green ones for strange quark matter. But on here, he's given some other general limitations on what we know, well, without doing any measurements. For example, this GR blue region is excluded because the star itself must lie outside its Schwarzschild radius, otherwise it would be a black hole. Similarly, you could just put in the pressure equal to infinity in the TOV equations, and you get that the mass and radius must lie below this light blue region, or you could put the speed of sound, which is dp d rho, the square root of dp rho has to be less than c, and then you get it has to lie below this. So we can easily exclude regions that lie to the left of here. Now it's more complicated here. There's general considerations. One thing you could do is look at rotational breakup. So you just spin this thing until it falls apart, and it turns out it's very insensitive to the equation of state. So to a few percent, you could just use basically a rotating fluid, and in this particular case, the fastest known rotating neutron star is this particular one, discovered by Jason Hessels about 5 years ago. So that means that it must lie above this green area. So we've got this exclusion. And these, there's a couple of other ones you could put on if some fast quasi-periodic oscillations. So this is at 716 hertz. These QPOs are at 1200 hertz, but it's not by any means certain that this is a rotational frequency. It may be an oscillation frequency in the crust, more likely. I think it's more likely. Okay, so we still got a wide range available for from what are fairly simple considerations and robust. Okay, so there are other, we can go to other things where we have more precise, some precise data. For example, masses have been measured for many radio pulsars in binaries. So here's a whole set of masses from double neutron star binaries, and a set from white dwarf neutron star binaries, and main sequence neutron star binaries. But the error bars tend to be large, except for this group here, and all the ones that are measured are very close to 1.4 solar masses. The limits for X-ray binaries depend on a lot more assumptions, and again, the error bars tend to be large, and even the best case, which is 4U1700, is only about less than 2 sigma away from 1.4 solar masses. So this has great promise, but so far there haven't been really good measurements. The most recent high mass radio pulsar isn't here. I'll mention it at the end because this is a graph made in 2007, but in 2008 there was one radio pulsar with a mass of between 2 and 3 solar masses, and I'll discuss the limits. So it's more than 3 sigma away from 1.4. Okay. Now I want to go to these millisecond X-ray pulsars, which are accreting matter from companions. So the general idea is you have an accretion disk, overflow of matter from some companion, and the matter goes down the accretion disk until it hits the magnetosphere, on the magnetosphere, surface of the magnetosphere, you thread the matter onto field lines, and then it free falls basically down onto the surface, following magnetic fields, and creates a hot spot on the surface. So in this hot spot, if the rotation and magnetic axes are misaligned, you get a lighthouse effect as it goes around. You could also, for the most accreting neutron, the classical accreting neutron stars are fairly high luminosity, so this hot spot should have a significant vertical extent, but if the luminosity is low, it's fairly simple, and the spectrum is well explained in terms of black body plus some Comptonization. So, okay, so we see this thing going around, but then you have to take into account the fact that the light that comes from the spot is affected by gravitational deflection. So here's an old diagram showing just a bunch of parallel light rays coming in from the left, and where how they get deflected. This circle is for 1.4 solar masses and roughly 14 kilometers, and the smaller circle is the same mass but 7.3 kilometers. That value is chosen so that a light ray coming in from infinity could come in and just graze the surface and then go back. So if your neutron star was as small as this, observer infinity could see light from the entire surface. Okay, so there would be basically no shadow zone. If there's no light bending, of course, the shadow zone is the entire back half of the star, but it decreases due to light bending. And we also get a magnified image because in this case, the observer would see the radius of the neutron star extending over this extent, whereas really it's only that big. So.
Does such a small radius violate any of the strong gravity?
Pardon me?
Does the 7.28 kilometer radius violate some of the fundamentals for using a mass radius?
Oh no, no. This okay. In terms of the Schwarzschild radius, this is close. I think it's close to 3m. Right. Actually, it may be a little bit more than 3m. I haven't looked at that recently. Okay. It's certainly the Schwarzschild radius is still somewhere down well within. Even below this, you can get multiple paths, but once you get inside this distance, you get some multiple paths, and then you get close to the Schwarzschild radius. Okay. So this thing is taking a 12-kilometer neutron star, 1.4 solar masses, putting a grid on it with 18-degree squares. So there's the pole, and you can see about 25 degrees beyond the pole on both sides, and the same on these limbs. And if you just move the spot around, okay, so the center of the spot is at 15 degrees. Now, how do I, wonder if I, nope, I have to go back. Oh, I guess I need to click it. There we go. So you can see that the magnification, the spot gets bigger, and you can see it well. You can see both spots at the same time, even though they're exactly antipodal, opposite sides. All right. So for millisecond pulsars, these were only discovered recently, and the first one was discovered in 1998. There are a couple of problems. One is just if you have fast pulsations, you need a high signal to noise to see it. Otherwise, you won't be able to get enough photons to measure the pulsations. And the other thing is that these sources are very faint. So they're about 1,000 times fainter than the bright X-ray pulsars. And you can see that here. Here's the count rate. Well, maybe a few hundred times greater. So this is 10 counts per second in the RXTE. Hold on. Okay, no, that isn't 10. Okay, so this is during a burst. During the burst, they can be comparable to a normal X-ray pulsar. But these bursts are fairly rare. They last for a couple of weeks and occur every several years. Okay. All right. So if these periods were actually expected for many years, the radio pulsars were discovered back in about 1980, millisecond radio pulsars, and it's thought that these things should be the millisecond X-ray pulsars would be the progenitors of millisecond radio pulsars. So these are predicted to exist for a long time, but not found until 20 years after the radio pulsars. Okay. And this is the discovery observation, which shows the flux in a burst which lasts about 20 seconds. And so the count rate goes up and down, and the left-hand axis is a power spectrum taken every second. So each second you take the Fourier transform of the count rate and get a power spectrum. And you see the frequency 401 hertz here in the tail of the burst, and in the rise of the burst it changes from roughly 398 to 401. Okay. Millisecond pulsars were hard to discover, but once we have them, we could work with them and see what we could learn about neutron stars. So the surface velocities turn out to be a fairly good fraction of the speed of light. So there are about 8 millisecond pulsars, anywhere from 200 hertz to 600 hertz rotation frequency. So this would be 500 hertz. Okay. So what it means is when the hot spot is moving towards you, it's boosted in brightness, the frequency goes up. All right, and when it's moving away from you, it goes down. So it should make the pulse shape asymmetric, and the asymmetry depends both on the speed, which you know because you measure the period, but you don't know the radius, so there's an uncertainty there. But it also depends on the pulse shape depends on the light bending as well. Okay. So hopefully you could separate these two effects. You also have time delays just for the light travel time from the light from the back to travel to the front. And that will make the pulse shape asymmetric. And the last thing is you have oblateness. Okay. So even if you have perfectly point-like or circular emission region, you get asymmetric pulse shapes. So a couple of things I've been working on with Sharon. One of them is this. There were pulse shape models done for millisecond pulsars without including oblateness because it was initially thought this isn't important, but it turns out it is quite important. So one can imagine that it's not so much the oblateness affects the light bending or affects the Doppler effect so much as it affects the visibility constraint for the surface. Okay, so I illustrate that here. So if we have an oblate star, it would be flattened, and the spherical star won't be. And one thing Sharon and I worked on was you take a whole set of equations of state, calculate rotating neutron stars with the RNS code, public domain code, which Sharon worked on. And then you could, for any given rotation frequency, then you could take the surface shape and fit it with a Legendre polynomial. And here's an example. So this is not unreasonable. 1.4 solar masses, 600 hertz rotation period. Then the oblateness, so this is the zero order polynomial, second order and fourth order. The oblateness is order of 10%. So this is exaggerated here, but you could see that if your observer off here, you could see a spot down at this latitude if it's oblate. So it's visible anywhere in this half of the celestial sphere, but if it's the same spot on a circular star would be visible to a different set of observers. So that affects the pulse shape, and here's a calculation for that exact star. So the models everybody had been using used a spherical surface, and this is the pulse shape you get. And if you use oblate surface, you get this. So we've got different things. We used full GR calculation where you use the GR metric for a neutron star and all the ray tracing in that metric. You get the red line. If you take the surface of the star to be the actual surface calculating using GR, but use a Kerr metric, you get the green line. And if you use the actual surface, but use the Schwarzschild metric, you get the blue line. So we also discovered that Schwarzschild metric is just as good an approximation to the exact metric as the Kerr metric. Right? Kerr metric's no better than Schwarzschild for this.
Exactly means you really solve exactly the metric outside the rotating neutron star.
Pardon me? Exact, yes, that's right. You solve for the metric is different outside, yeah.
So the deviations from Kerr.
Yeah, there's the deviations from, the deviations from Kerr.
But not just the blatant,
There's frame dragging. Schwarzschild has no frame dragging, but Kerr has the wrong frame dragging.
Right.
So it's not that much better. But frame dragging is small, so it doesn't really matter. That's not the main effect. So we've done a whole bunch of different cases. The differences between Kerr, Schwarzschild, and the exact are always similar. So usually, I mean, Kerr might be a little better, but it's not, if you expand it in orders, it's not any better to lowest order. So there's no point in using it. You better go to the exact. The only problem with exact is you have to do a full numerical solution, and it takes a long time in a computer. You don't have any analytic way of doing it. Okay, and then these are just the other ones. So that makes a huge difference.
Sort of, you can get something done.
Pardon me?
The ray tracing in Kerr is almost as easy as Schwarzschild.
Right.
It has some extra.
Yes, just analytic, yeah.
Whereas,
Yes. So it's a lot of work to do the full one, yeah.
well, no, the ray tracing in Kerr and Schwarzschild, you don't even do it.
No, you just do it's an integral, right?
And born here, it ends up there. You know.
Yeah. Okay. Okay. So we have this code for doing the full calculation, but it takes an awful long time to run. So it's okay to calculate a pulse shape, but it's no good for doing fitting, because in doing pulse shape fitting, you need to run this thing thousands of times, right? You've got, there's a 10 or 15 dimensional parameter space, and you need to explore all these dimensions. Okay. So a couple of papers, we made various approximations. You can do expansions and get analytic formulas and get a practical method. So it's still, you get basically a power series expansion for various things, including the shape of the neutron star as a function of various parameters like the mass, the radius, and the rotation period. And you also get the correct light aberration effects. Like all of that is, if you have the full metric, it's all included in the metric, but things like the light aberration and the Doppler boosting are all included in the following the geodesics, but you have to convert those into something that's more easily calculated. Okay, so we've done that, and we applied this to the original outburst pulse shape from SAXG 1808 from the 1998 outburst, and compared that to the first modeling of that pulse shape by Putanen and Gerlinski in 2003. So their results are given by these little bars, and our results, when we omit the oblateness and time delays, we get a 3 sigma allowed region over here and a 2 sigma allowed region here. Now, if you go with their paper, it's completely consistent with this, because this one, they put it in their paper, but it's not allowed, right? It's one of their solutions that the fit was too bad, and this one is just barely allowed at 3 sigma, so their 2 allowed ones are these ones. Okay. But they knew it wasn't allowed, so they didn't actually say it in the paper, right? They've got the numbers there, but they didn't emphasize it. All right. Now, the thing we were quite dismayed to find is when we put in the oblateness and the time delays, our 3 sigma allowed region shrank to this, which is totally unreasonable to compare to any of the equations of state. So, actually, it took us a couple of years to figure that out, but I'll describe that in a few minutes after I describe some other fits. It's because the pulse shape is time variable, and this, well, one of the reasons is it's time variable. So that if you average a bunch of pulse shapes and fit it, you don't get the same result as fitting the pulse shapes, right, that are separately. Okay, here's another object. Okay, so there's about 8 of these things, but there's only a couple that have that are bright enough to have good pulse shapes measured. So this particular one, here's the pulse shape in one energy band, 7 to 9 keV. Okay, part of what's done, if I go back here to Whoops, I missed it. Here. Okay. Part of what's done in this is we know that the spot model has a black body component and a Comptonized component, and they have different angular distributions. So you fit a high energy band where the Comptonized component's more important, and you fit a low energy band where the black body is more important. And they have different pulse shapes, but so you can get better constraints on it. So that's done here too, but only.
How do you know the angular distribution of the Comptonized component with that?
You don't really know it well, but you use the Sunyaev and Tacharchik approximation. Well, I mean, it depends on the electron scattering optical depth and the Compton Y parameter, but we just use we keep a free parameter in there to allow for different values of different amounts of comptonization. So that's a free parameter and it fits.
But also, as material slides onto the surface of the neutron star.
Well, we're assuming that it's a homogeneous spot, and we're only allowing one free parameter to allow for all of that. So basically, you can think of it as the Y parameter.
You're taking stuff to fall on the pole, etc.
Right. Well, yeah. Well, we're not fitting the burst pulse shapes. We're only fitting the steady, the pulse shapes, which are much more lower luminosity. Okay. So what I wanted to point out here is we tried fitting it, and it looks like there's a bump here for this object. So, okay, all the parameters you need are the mass, the radius of the neutron star, the angle, the inclination, which is the angle between the observer and the rotation pole, theta, which is the angle between the rotation pole and the hot spot, phi, which is an arbitrary rotation phase, and some intensity parameter, and then an asymmetry parameter for the Compton scattering. Okay. And then if you have a second spot, you have all these spot parameters for the second spot. So it turns out this is much better fit by a two-spot model where the second spot is only visible for a limited range of rotation phase. So what we did, okay, so we did a two-spot model because the one-spot model wasn't acceptable. And then because you introduce all these other parameters for the second spot, but it's only 6 data points, it makes more sense to throw out these data points and to fit a one-spot model to the rest. It's just.
You're taking the center of the magnetic dipole?
No. Well, the second spot is arbitrary location. But
How are you choosing the size of your spots?
well,
Does that matter?
it doesn't matter a lot. In this case, we chose a spot which was, its diameter was, okay, it's a 3-kilometer spot diameter, but the neutron star radius is 50. Okay, so it's about 10% the diameter of the star. And we did the calculation both with a point and with an extended spot, but it didn't make a significant difference. They both give the same result. It turns out the shape doesn't depend much on the spot size. It depends a lot more on the emissivity, the angular distribution of the Compton scattering, and it depends on the position of the spot critically, as well as the light bending. So we've done the calculations for both point spots and spots as big as 3 kilometers in diameter. Okay. It's not expected to be bigger than 3 kilometers based on the luminosity.
Is your compensation model involving an extended screen that goes over a range of radii?
No, it's just a single, just right at the surface. Okay. Right. So what we did was it made sense that this was due to a second spot, but since there's only a few data points for the second spot, we fit the pulse shape and excluded these points. Okay. So that's what this dashed line here, it's the one spot, best fit one spot model excluding these points, which the extra emission here is due to the second spot, which you just barely see behind the star. Okay, and then what we got out of this was high mass and large radius, which again, it doesn't work very well, right? So something's wrong.
Well,
Okay. I remember for SAXG 1808, it's something like between 10 and 20 degrees, 3 sigma, from the pole. Okay. Part of the reason they're that large is they're roughly 10 parameters that go into the fit, and we do the full covariance. That's what takes all the time. And each fit with this model might take 15 minutes, but to explore 10-dimensional parameter space usually takes a couple of months. Right. Okay.
And these sigmas are all the other parameters are allowed to vary over
Yeah,
sigma.
yeah. Everything's allowed to vary. So when we're varying mass and radius, we do a fit at each point. So we do a whole grid of fits, allowing all the other parameters to vary.
And sorry, when you do this fit, what metric model are you using?
Pardon me?
What metric model are you using?
Oh, just Schwarzschild, but with the oblate surface. And the oblate surface comes from the RNS code. Okay. So we use the RNS code to give the, right. Okay. And this is just an aside because this is work I did before I even met Sharon, is working on pulse shape fitting for slow pulsars. In this case, because it's high luminosity source, the accretion columns are tall, and we know the geometry fairly well because the pulse shape has been studied, for 20 years, and many people have worked on it, and so we got the geometry down very well for the accretion column. And what I did was put the emission surface to follow dipole field lines, use some of the geometry constraints from the pulse shape evolution. So this doesn't allow much freedom. So there's not much uncertainty in the geometry, but there's still the emissivity, there may be some uncertainty. So you get a fairly good constraint on the mass to radius ratio, but no direct measurement of mass or radius because it's not moving fast enough to separate the two. It only depends on m over r, not on m and r separately. But mass is known from the orbit. So this just shows a nice fit to the pulse shape, and it actually works, the same model will work in all 6 energy bands. So you could observe the pulse shape in 6 energy bands, and you get good fits in all of them. Oh, it's the disk, because you've got an accretion disk, which is gradually, it's like a screen gradually covering the extended emission region. So you can see the column being cut off.
Is this like this is just
Yeah, the accretion disk is rotating at a different period than the orbit, so that your viewing changes over 35. It repeats every 35 days, the viewing constraints. But it's.
Is this like this radiation-induced warping, or?
Yes. So the model is this Wiegers and Pringle radiation. But that doesn't really matter. You just take the geometry of the disk, regardless of the mechanism, and then. Although there's other disk models that can't produce the warping, and anything that doesn't produce the warping, I think, isn't viable in this case. Okay, so I said something about time variability. So the pulse shape varies a lot. Here's the 1998 outburst. So this is called an outburst, but there was a bright burst, like an X-ray burst, thermonuclear burst, which is what the discovery was. And then after the burst, the source is bright. So the thermonuclear burst is really bright, but this bright part here is where the source is only about 100th as bright as a typical X-ray pulsar like our X1. So these pulse shapes vary a lot. And out of all the ZUA pulse shapes, we picked the 7 statistically best ones to study and fit with a single model with a fixed rotation axis, fixed mass, and fixed radius, but variable hotspot location and variable emissivity. So the compensation parameter changes with time as well as the position of the hotspot on the star. Okay. So we tried fitting these together. I found out there was some extra externally scattered X-rays that had to be put in, or else you couldn't consistently fit these different pulse shapes. Okay. So here's an example of 4 of the pulse shapes. There's a low energy band and a high energy band. The low energy band is this one, 3 to 4 keV, and this is the 9 to 20 keV one. It's not obvious here, one circles and one squares, but it doesn't really matter. So we could fit all of these pulse shapes with a single mass and radius and inclination angle. And the results for that, so they're done in pairs. So far we haven't done them all 7 simultaneously. That's the next thing to do. But we've done in pairs, and they all give basically the same results. We constrain the inclination angle to be less than 9 degrees, but that's natural because you're seeing a system with an accretion disk, and so you're only going to see the spot on the side, on the star, of the side of the star which is closer to you. So there could be a second spot with angle. So the inclination angle from the observer to the opposite end of the rotation axis. So this just means the observer. You've got two rotation poles, right? So this is the near rotation pole. Okay. So this is 2 sigma limits and 3 sigma limits. And we were surprised actually to find out that they were bigger than before, but I think that's just the time variability. So you get a nice region, but it would be nice if it was smaller, but it's pretty big. If you go to the literature, there have been lots of optical studies of this system, but they're contradictory. Here's one with a mass function is less than 0.1 solar masses, and they get an upper limit on the X-ray source of 1.6 solar masses. Another study got a lower limit at 2.2 solar masses, and then there's other studies on the inclination angle of the system. So this hasn't really been resolved yet. But what we've done is if we constrain the inclination to be less than 70 degrees, it cuts out a fair amount of this. I think I can go back there. And so you get a smaller allowed region. So again, this is the 2 sigma region's pretty small, but 3 sigma is allowed a lot. Hopefully better data will change that for more outbursts. Okay, so that's all we have. This is the most recent thing we have. And what I wanted to do was to put them all together. So here's the XT J1814. Here's roughly what we have for SAX J1808, and here's Hercules X1, along with equations of state. Now previous equations of state were plots for made for rotating neutron stars with the rotation frequency of that particular one. But in this one, these are non-rotating ones because we're trying to compare. But they're not much different, right? So it's not a fair comparison because, for example, given this equation of state will vary, the mass-radius relation will vary with rotation frequency a little. So the curve to compare with this one at 314 hertz would be different than this one at 401 hertz and this one at some low frequency, but I haven't put that in. Okay, so it looks like quite a mess, but if you look at it, at 3 sigma, there's nothing that fits them all. The closest one is this APR. It goes through the allowed region for these 2 and close to the allowed region for this one, or some quark star equation of state comes very close to the allowed region here and goes through these 2. So it's still possible. I think we really need, what we need to do is redo this one, put in some scattered light and see if that brings it down. Because this analysis doesn't include scattered light yet. So that has to be done yet. It may bring it down. Otherwise, so this APR and this Q140 are close to fitting all 3. Okay, but because we have quite different allowed regions.
Your emission models predict any dependence of the pulse shape on accretion luminosity?
On
Accretion luminosity?
well, only in the sense that the emissivity and the spot size would change. Okay, but we're taking a phenomenological model for the componentization. In the sense, we're just thinking it to be a free parameter.
Well, I guess what I should ask first, does the pulse shape change much with luminosity?
But with these ones, yes, it does. Okay, I guess that's something I'm really, if we go back and take all of these, the main thing that happens, the biggest difference between this is just the different distance of the spot from the pole. So for the 1998 pulse shape, which has the largest modulation, the distance from the pole is 18 degrees, plus or minus 3 or 4 to 5 degrees, and the other one's about 12 degrees, plus or minus 3 or 4 degrees. So the spot just moves close to the pole. Fred Lamb has a paper out where he has this burying of, I think the idea is it's magnetic field burial, and then when you have low accretion rate for a while, a magnetic field can emerge more and it pushes the spot away from the pole. Anyways, that's, no. Okay. All right. So it's getting to the point where it'll be closer. I think that what's missing here is need to redo this model with the scattered light to see how it affects the boundaries. Because if it moves the boundary zone a little, it could change your conclusions. So that hasn't been done yet. All right. So this is just a list of some of the things. And here I mentioned this high-mass radio pulsar in a globular cluster from Paulo Freire. Now, there was an earlier one published and retracted, but this one still stands. So here he's got his probability distribution from the paper for the mass. And he in the abstract, he lists a 1 sigma limit, but the 3 sigma limit is still above 2.1 solar masses with no radius measurement. So again, if you go back here, that's this line here. So you could see that if with that line, still it's close to these two, right? So it doesn't really alter this conclusion. Okay. The other thing is that they may be all in the same equation of state, or perhaps there's 2 different equations of state, and we have 2 different types of objects, some neutron stars and quark stars. So you have a mixture, and that's, if you have a phase transition, that's certainly possible to have 2 different types of stars in existence. And of course, there's also possible some small errors in any of the above determinations. Okay, so I think the whole thing.
Why did we get upper bound on N and R for 1808 and a lower bound for 1814?
Okay, so it's the modulation. So qualitatively, where do I go to the pulse shape? These pulse shapes are fairly smooth, and to get the asymmetry, you need to have a fairly high velocity, and with this high velocity, if you didn't have the light bending, it would be more asymmetric. So light bending smooths it out, and the high. This is 400 hertz, right? And J1814 is a lower speed. So it has to be a larger radius to get the asymmetry in that one. I don't know if I showed the pulse shape. Oh, yes, of course I did, right here. So this one, for 300 hertz, has to be a fairly large radius. Otherwise, the light bending would smooth it out. Because you basically know the Doppler effect because you know the frequency. I mean, they both depend on, both of these depend on how far it is from the pole. But it's all folded in.
You showed only one light curve here.
Yes, this.
But it does change.
Yes, it does change, and what this is from taking the 2 days out of well, it was observed for 10 days during outburst, and we took the 2 days of the best pulse shapes. So another thing that could be done with both of these is to take. Okay, well, it's not. These are highly variable. Like you could easily see by eye with. 1814, they look by eye the same, although if you do the chi-squared, they're different. So it doesn't vary much. But we could, instead of just doing 2 days, we could jointly fit all 10 days. But then doing the error analysis is not feasible. And there's no point doing a fit unless you do the error analysis. So we're rewriting the code to try to make it more efficient so we could simultaneously fit all of them rather than just do it pairwise. It may or may not make much difference, but it should help. I think the best thing that will help is to have a bright outburst where the error bars on the pulse shape are small. So that's really the problem. Is they're not high precision like Hercules X1 is. Well, partly because it's brighter, but because the period's longer, you get better statistics.
So, and then when you get different pulse shapes, you see different pulse shapes in two bands. So, what is different about geometry in those two bands?
Oh, we're assuming the spot geometry is exactly the same, just that one is black body where it's isotropic, and the other one is Compton scattered. So that's critical. Angular distribution. Okay. Yeah. Okay. So there are assumptions in there, but we could also test these assumptions by varying the emissivities and seeing how that affects the results. Okay.
And you have to vary the angular distribution of the compromised component.
Yes. Well, we have
from one bit to another in order to get it.
Yes. It varies by a little bit. We have this parameter, so we fit the Sunyaev-Tatarchik distribution versus angle as 1 minus a cos theta. And the a varies from, let's say, 0.6 to 0.75. So it varies a little bit, but not a lot.
So physically you're varying the temperature, or does this model assume an isotropic angle distribution of the particles with respect to magnetic field, for example?
We're assuming that there's no magnetic effects on the emissivity. I mean, the magnetic fields are low for this.
That's fine, but,
Right.
That was just one way of phrasing it. But, I mean, it's basically locally, it's a Maxwellian distribution.
Yeah. Well, I think if you look at the magnetic fields for these are about 10 to the 8th Gauss, and the temperature, electron temperature, is about a keV. It shouldn't be a strong effect.
No.
You're not talking about that?
It's just so much what was in the model.
Yeah.
So
Okay. So it's problem logical, but the emissivities we get are consistent with what you expect for comptonization. That's no proof. It just means that you can't say anything wrong with it. Right? It doesn't mean it's right. Just that there's nothing obviously wrong. Okay. So we're going to continue on this, and so the two goals are doing both these systems, because so far there have been new millisecond X-ray pulsars, but they've all been so faint that they won't give any useful constraint, or else they don't have, if they're too symmetric, then they don't have any asymmetry. You can't fit anything.
with the transients, once the accretion turns off, they're too dim.
Oh yeah. Well, even these ones, these are all the millisecond X-ray pulsars are transients.
But I mean, when you're at the phase where you think it's predominantly just a cooling spot.
Right, outside of X-ray burst. We're doing it outside of X-ray burst. We're not pretending to do anything with the burst observations.
Just technically, you can't do this type of precision pulse shape fitting when the accretion is turned off and you just have some residual emission from the.
Right. Okay. Well, I suppose it would be possible to do. Actually, is it some pulse shape fitting on thermal neutron stars? But then again, I think that the asymmetries they're not rotating fast enough, and there's no asymmetries. If you've got a flat surface on a slow rotating star, there's so little. There's not enough information about M and R separately to get. Like with Hercules X1, the only thing you could fit was M over R. Okay. You need the rapid rotation to break the degeneracy.
Unless you know how far away it is.
You mean in terms of using the flux as well, or? Yeah. Well,
Inside the spot as well. Huh? You know, inside the spot as well.
Yeah, but the size of the spot then goes into what the pulse profile.
yeah, you have to have you have to have a very good emissivity model. I mean I think.
But here you're pretending to do too, right?
Yeah. Well, except we haven't assumed anything about the normalization. I mean, we know from spectral fitting the normalization is about right for, you know, a 1 or 2 or 3 kilometer spot on something that's a few kiloparsecs away. But we don't use that information.
But you're assuming that whatever's on the surface is isotropic, for example.
Well, we're assuming the black body part is isotropic and the Comptonized component has a Comptonized distribution.
But you're assuming it's a black body is what you're saying. Okay.
Well, not only assuming it, it's been measured in the X-ray spectra.
That looks vaguely like a black body.
Well, I think fairly well with Chandra.
You are assuming isotropic. I mean, I think you already answered this question, but
Homogeneous spot.
well, that, you know, the Chandra distribution of particles is how about isotropic distribution function?
You mean for the Comptonization? Yes, we're just assuming that it's...
And so it has basically the same angular set as the black body spot.
Yes.
And you just put this electron cloud on top of it in a thin layer.
Yes. Yeah.
And so the only one parameter you really have then is the two parameters off of that and KP.
Yes, but we're just using a single parameter to, based on the numerical those old numerical calculations of Sunyaev and Starchik. Yeah, which seems to fit fairly well a single parameter. I mean, really, there's 2 parameters physically, but phenomenologically, it's very closely approximated by 1. Yeah, the electron temperature is known pretty well anyway, so that's not, it's the optical depth that's not known.
And you get very good bits.
Pardon me?
You get very good bits with this type of model.
Yes, yeah. Okay, I mean, I think that the part of the, one thing that we're hoping there would be a lot more data to work with, but so far there's only these 2 that have good enough pulse shapes to work with. There may be more come. I mean, these systems roughly outburst once every 2 years, and if there's 2 to 3 years, and if there's 6 of them, then there should be a lot more coming. But then RXT is pretty well dead, so we have to wait for... Well, yeah, but it's operating on 1 detector, which isn't operating perfectly well, right? So it's... Yes, AstroSat, that's right. Yes. All right.
Any questions for Denis?
I think those were the questions. I just want to make sure everybody has a chance. Right?